This slide introduces the concept of panel cointegration estimation. The core message is that cointegration helps us identify long-run equilibrium relationships, even when dealing with chaotic and non-stationary data. This approach is crucial for identifying stable economic signals amidst fluctuating variables. We will delve into the theory and practical application of FMOLS and DOLS methodologies to achieve robust empirical results. A common issue with economic panel data, like GDP or investment, is that it is often non-stationary, specifically integrated of order 1, or I1. This means it has a stochastic trend. If we apply standard OLS to non-stationary variables, we fall into the trap of spurious regression. This gives us a high R-squared and seemingly significant t-statistics, but the relationship is completely meaningless. To address this, we need specialized estimators like FMOLS and DOLS, which are designed to handle the endogeneity and serial correlation biases that arise from non-stationary data. The first step is to formally test if our variables are non-stationary, or I1. We use panel unit root tests like the IM, Passarin, and Shin, or IPS test, and the Levin-Lin-Shu test for this. Once we've confirmed the variables are I1, we must then test if they are cointegrated, meaning do they share a common long-run trend? Tests developed by Pedroni and Call are standard for this purpose. Only after confirming cointegration do we proceed to the final step, estimating the long-run coefficients. This is the main focus of our lecture, where we'll use methods like FMOLS, DOLS, and CCR. This slide introduces the theoretical equation that forms the foundation of our cointegration analysis. The equation is given by YIT equals alpha I plus beta XIT plus UIT. Let's break down each term. First, alpha I represents the individual fixed effects, or heterogeneity. This term captures different baseline levels across countries or individuals in our panel, allowing for unique intercepts for each unit. Next, beta XIT contains beta, which is the co-integrating vector. This is the core long-run parameter we aim to estimate. The assumption here is homogeneity, meaning this long-run relationship is common across all groups in the panel. Finally, UIT is the stationary error. This term represents the deviation from the long-run equilibrium. For cointegration to exist, this error term must be stationary, or I0, indicating that the variables eventually revert to their long-run relationship. On the right side, the assumption for this model is that we assume a common long-run relationship beta across groups, but allow for individual intercepts alpha. FMOLS uses a non-parametric approach. It modifies the variable data before estimation, using kernel estimators to correct for serial correlation. In contrast, DOLS is a parametric approach. It modifies the regression equation during estimation, adding leads and lags of different regressors. To summarize, FMOLS corrects the data, while DOLS corrects the equation. Both methods are designed to fix endogeneity bias in cointegrating regressions. This equation shows the Dynamic OLS, or DOLS, model. The new summation term, sum from j equals negative q to p, Cij delta xit plus j, is crucial. It includes leads, j greater than 0, lags, j less than 0, and the contemporaneous value, j equals 0, of the first difference of our regressor, delta xit. The primary purpose of these leads and lags is to absorb any endogenous feedback from the cointegrating relationship. By explicitly modeling these dynamics, we make the error term epsilon it orthogonal, or clean, ensuring the estimates are unbiased. However, there is an important trade-off. Adding each lead and lag consumes observations, thereby reducing your degrees of freedom. This can be particularly challenging in panel datasets with a limited time dimension. Despite this, DOLS is often more robust in smaller samples, making it a valuable tool, though it's important to be mindful of the observation cost due to its lag lead requirements. Before any estimation, you must tell EViews that you are working with panel data. This is a critical prerequisite. In the workfile structure dialog, you must select Dated Panel. Then you need to specify the series that identifies the cross-section, like ISO code for countries, and the series that identifies the date or time period, like year for year. Always double-check the range description at the top of your workfile window. It should clearly state the panel dimensions, for example, 1950-2000 x 208, which indicates the time period and the number of cross-sections. If you forget this step and leave the data unstructured, EViews will treat all 10,208 observations as a single time series, and all panel-specific commands and tests will fail or produce incorrect results. Once the data is structured, we can navigate the menus to find the correct estimation tool. To begin, you can access the Panel Cointegration Estimation tool through the main EViews menu. Navigate to Quick, then select Estimate Equation. Once the equation estimation dialog appears, it is crucial to change the method from the default LS, least squares, to COINTREG, Cointegrating Regression. This step is critical because the COINTREG method is specifically designed for cointegrating relationships and is distinct from standard OLS. Selecting COINTREG will unlock additional specific tabs within the dialog, allowing you to configure settings for long-run variance and lags, which are essential for both FMOLS and DOLS estimators. For those who prefer command line execution, the syntax for estimating an FMOLS model would look like this. Equation eq1.cointreg method equals FMOLS, y x1 x2, where y is your dependent variable and x1 and x2 are your cointegrating regressors. Unlike standard OLS estimation, where all variables are listed together, the COINREG dialog requires you to separate them. You must input your dependent variable, in this case LTFP, into the Dependent Variable field. All independent variables, like LRD and LFRD, should then be entered into the Cointegrating Regressors field. This distinct separation is crucial, as it instructs EViews on how to apply the specific algebraic transformations necessary for panel cointegration estimators, like FMOLS and DOLS. This slide details the options for FMOLS, specifically related to the long-run variance calculation. The kernel option, often set to Bartlett, determines the shape of the weights used in the heteroscedasticity and autocorrelation consistent, or HAC, variance estimator. The bandwidth setting is crucial as it determines how many lags are included in the calculation to correct for serial correlation. For most users, NUI West automatic bandwidth is recommended, as it's considered the safest and most robust choice, automatically selecting the optimal number of lags based on your data. For DOLS, the Options tab is where you specify the number of leads and lags to include in your model. You can choose Fixed to manually define the number of leads, P, and lags, Q. This is useful if a particular paper specifies exact lag structures for replication. Alternatively, you can have EViews select the optimal number of lags automatically based on an information criterion, like the Akaike Information Criterion, AIC, or the Schwartz Information Criterion, SIC. However, a crucial warning: be extremely careful not to set the maximum number of lags too high, especially if you have a short time series, as this can quickly consume all your available degrees of freedom and make estimation impossible. For our case study, we'll use a classic dataset from Cao, Chang, and Chen, 1999, that examines the impact of R&D on productivity. The dependent variable is LTFP, which is the log of total factor productivity. We have two regressors, LRD, the log of domestic R&D investment, and FRRD, the log of foreign R&D investment, which captures knowledge spillovers. The central hypothesis is whether domestic and foreign R&D investments have a positive and significant impact on a country's productivity in the long run. The data covers 22 countries from 1971 to 1990. This slide outlines the step-by-step execution for our analysis. First, select the method as Cointegreg. Second, choose the estimation setting as FMOLS. Third, set the regressors to LRD, LFRD. Fourth, specify the trend specification as constant level. Finally, and this is crucial, navigate to the Options tab and set the bandwidth to user-specified equals 6. It's important to remember that replicating academic papers often involves fine-tuning these options, such as bandwidth or kernel type, beyond just the basic equation variables. Here we see the FMOLS results for our R&D case study. The coefficient for LRD, log domestic R&D, is 0.125. The coefficient for LFRD, log foreign R&D, is 0.089. Both coefficients have very small p-values, 0.00 and 0.045, indicating they are statistically significant at the 1% and 5% levels, respectively. Since our variables are in logarithms, these coefficients represent long-run elasticities. The result means that a 1% increase in domestic R&D is associated with approximately a 0.125% increase in total factor productivity in the long run. The R-squared of 0.76 indicates a good fit for the long-run relationship. This is the most critical validation step. The entire theory of cointegration rests on the assumption that the residuals, the deviations from the long-run equilibrium, are stationary, or I0. After running the regression, you must save the residuals as a new series. In EViews, you can do this via the Proc menu and selecting Make Residuals. You then must perform a panel unit root test on this newly created residual series. If the panel unit root test shows that the residuals are stationary, I0, your model is valid. If the test indicates the residuals have a unit root, I1, then your finding of cointegration was fake, the model is spurious, and the coefficients are meaningless. Imagine you find a significant relationship between two variables, but the residuals from your model show a clear upward trend. This means the model is systematically failing to capture the underlying dynamics, and the relationship is not a true long-run equilibrium. The unit root test formalizes this visual check. Having walked through the entire process from theory to validation, let's summarize the key takeaways and best practices. To summarize our discussion and highlight best practices, first, always check for unit roots in your variables, ensuring they are I1 before proceeding with cointegration analysis. Second, for robustness, it's advisable to compare results from both FMOLS and DOLS estimators. When using FMOLS, always opt for an automatic bandwidth selection like NUI West. Crucially, do not interpret the estimated coefficients as short-run dynamics. They represent the long-run equilibrium relationships. Finally, be mindful of potential cross-sectional dependence in your panel data, as ignoring it can lead to biased results. Remember, panel cointegration is a powerful tool, but it demands a strict process. Test for unit roots in cointegration, then estimate the long-run coefficients, and finally, validate the model by checking residual stationarity. This slide provides a summary of the EViews syntax for cointegration regressions and lists key literature references that form the theoretical basis of these methods. For EViews syntax, to perform a fully modified OLS, you would use eq1.cointegration method equals FMOLS y x1 x2. For dynamic OLS, a common approach is eq1.cointegration method equals DOLS lag equals AIC y x1 x2, where lag equals AIC automatically selects the optimal number of leads and lags using the Akaike information criterion. The key literature